On behalf of Indira Gandhi National Open University, we welcome you for this video lecture session. Today's topic is control charts for attributes. This is the 20th module for the course Quality Engineering and Management. I am Subhashish Maji, professor in School of Engineering and Technology from Indira Gandhi National Open University. Dear learners, let us start with our topic, that is control charts for attributes. After listening to this video lecture, you will be able to understand the control charts for attributes. You will be able to know the P chart, NP chart, U chart, C chart and Q sum chart, and you will be able to solve the numerical on control charts for attributes. The control charts for attributes are essential for those quality characteristics that cannot be measured physically, but such characteristics can be classified into one or two classes, usually defectives or non-defectives. For example, the presence of hole in an aluminum sheet classifies the item as a defective. When the quality characteristics of an item is measured by attributes, the control chart based on refraction defective can be used. For example, in a process running with a 2% defective rate, a mean of 2 defects per sample requires a sample of at least 100 for recording purposes. The calculation of control limits for attributes depends on two factors: whether numbers for constant size or proportions for varying sample size are being plotted. Number 2, whether defective items or defects are being considered. An item is considered to be defective if it fails to meet a required standard due to presence of defects. Thus, there are two types of control charts for defective items based on whether the sample size is varied, that is P chart, or constant, that is NP chart. Also, based on the presence of defects, charts are constructed for varying sample size, that is U chart, and constant sample size, that is C charts. In this lecture session, the construction of above mentioned charts and their utilization in statistical process control shall be discussed. The P chart is used for process control of defectives when it is not possible to take a sample of constant sample size because the sizes of samples are varying with time. Typical examples include arrivals of mails in post office without the PIN code number, scratches in glass sheets, holes in castings, etc. In such situations, the control limits are drawn for the average fraction defective, that is P bar. Before establishing the control limits, it is essential to have at least data for 25 subgroups. The first step in setting this control chart is calculation of fraction defective for each subgroup. This is given by P is equal to number of defects in each group divided by number inspected in subgroup. In that way, we can calculate the value of P. This enables to calculate the average fraction defectives, that is P bar, that is defined as the ratio of total number of defectives during period and total number of items inspected during period. The lower and upper control limits for P chart are given by LCL equal to P bar minus 3 under root P bar multiplied by 1 minus P bar whole divided by N cap. The UCL is equal to P bar plus 3 multiplied by under root p bar multiplied 1 minus p bar whole divided by n cap. Here LCL denotes the lower control limit and UCL denotes the upper control limit. So once you calculate the p bar, you can easily calculate LCL and UCL because p bar and n cap are known. Here n cap is the average of all sample sizes that are being inspected during a given period. If the calculation of lower control limit yields a negative quantity, LCL is treated as 0 because a negative limit on fraction defective does not make sense. So, dear learners, first of all, you have to calculate LCL, you have to calculate UCL, but in any problem, if you get the value of lower control limit as negative, then you have to take the value of LCL is equal to 0 because if the negative defectives does not carry any sense. The P chart is now constructed with center line P bar and each subgroup fraction defectives P plotted to see if they are lying within the lower control limit and upper control limit. Those fraction defectives lying outside the control limits are eliminated and the value of P bar and control limits recalculated. For example, consider the number of defectives found in 20 samples as shown in table 6.4. The sample size is 50. This is a table showing defectives D found in 20 samples. So dear learners, how many samples are there? There are 20 samples and D is the number of defects in each sample which is given in this table. So for sample 1, number of defects is 2. For sample 2, the number of defects is 3. For number 3, the number of defects is 4 and so on. First, the fraction defective in each sample or subgroup is found from equation 6.17. The first fraction defective is 2 by 50 because in sample number 1 the number of defects is 2. So the first fraction defective is 2 divided by 50, that is 0.04. The other values are being calculated on the basis of number of defects divided by 50 in each and every sample. So we will construct a table by finding out the number of defects in sample. Now the total number of defectives in these 20 samples is 40 because if you count the number of defects for 20 samples, that comes out to be 40, the sum of all values in second row of table 6.4. Now we can very well calculate the P bar, that is equal to total number of defects during period divided by total number of items inspected during period. But here you see that there are 20 samples and each sample contains 50 units. So P bar is equal to 40 divided by 20 into 50, that comes out to be 0.04. Now once you get the value of P bar, there is no problem for calculating lower control limit, that is LCL. So for this particular problem, the lower control limit is equal to 0.04 minus 3 under root 0.04 multiplied by 1 minus 0.4 whole divided by 50, that comes out to be minus 0.04. Dear learners, we have already mentioned that if you get the value of LCL is equal to minus terms, then you have to take the value of LCL as 0. Now for UCL, we can calculate as UCL, that is upper control limit, that is equal to 0.04 plus 3 under root 0.04 multiplied by 1 minus 0.4 divided by 50, that comes out to be 0.124. But after calculating, you must see whether any value you are getting more than the upper critical limit. Now let us see how we can proceed for this numerical. Now dear learners, you see the table, you will observe that the fraction defective of 17 point is 0.14, that is greater than upper control limit. Hence, this subgroup, that is the 17th sample, that is the 17th point, having 7 defectives is discarded. So you have to discard the 17th sample and you have to remove the 7 defectives from the total number of defectives. So you have to recalculate after leaving that particular sample. So previously we were having 20 samples. So if you discard one, so number of samples will be available 19, that is 20 minus 1, 19, and the number of defectives will be 40 minus 7, because previously there were total number of defects were 40, including the 7 defectives which are at the 17th point. Now we are not considering the 17th sample. So 7 defectives will be out from our calculations. So new P bar is equal to 40 minus 7 divided by 19 into 50, that comes out to be 0.0347. Now once you calculate P bar, you have to recalculate the upper control limit and the lower control limit. So the new limit or LCL, that is lower control limit, is equal to 0.0347 minus 3 under root 0.0347 multiplied by 1 minus 0.0347 whole divided by 50, that comes out to be minus 0.430. And as we have already discussed that if you get the lower control limit in any point is minus of something, you have to take LCL as 0, and you can calculate the upper control limit is equal to 0.0347 plus 3 under root 0.0347 multiplied by 1 minus 0.0347 divided by 50 is equal to 0.113. Now you see that you have got the values for LCL, that is lower control limit, is 0, and the upper control limit you have also calculate. So any point which is within this range is acceptable. Now let us discuss about NP chart. The NP chart is similar to P chart, the main difference being that the sample size is constant. The data values plotted are the actual number of defectives per sample or subgroup denoted by NP. The control limits are given by lower control limit is equal to NP bar minus 3 under root NP bar within bracket 1 minus NP bar whole divided by N cap, and upper control limit is equal to NP bar plus 3 under root NP bar multiplied by 1 minus NP bar N cap, where NP bar is the grand average of all defectives. So NP bar is equal to total number of defectives divided by the number of samples inspected. So once you calculate NP bar, there is no problem for us to calculate the lower control limit and the upper control limit. So any value which falls within this range, that is acceptable. And one thing is very important, that while calculating LCL, if it comes out to be negative, you have to consider as 0 for that particular case. Now let us discuss about the U chart. The U chart is used for process control for defects when it is not possible to take sample of constant sample size. This chart puts a check on the proportions of defects per sample. Hence, unlike P chart, it deals with the number of non-conformities per item within the sample. For example, the number of holes in a casting. If there are more than specified number of holes in the cast product, the product is termed unfit. The control limits are given by LCL, that is lower control limit, is equal to UR minus 3 under root UR multiplied by 1 minus UR divided by N cap, and UCL, that is upper control limit, is equal to UR plus 3 multiplied by under root UR multiplied 1 minus UR divided by N cap. For U chart, the control limits are given by LCL and UCL, where N cap is the average of all sample sizes and U bar is given by U bar is equal to total number of defects divided by total number of items inspected. Now let us discuss about the C chart. The C chart is used for process control of defects when it is possible to take samples at a constant sample size. The data plotted on the chart are number of defects C in each sample. The control limits are given by LCL, that is lower control limit, is equal to C bar minus 3 multiplied by under root C bar multiplied 1 minus C bar divided by N cap, and the upper control limit UCL is equal to C bar plus 3 multiplied by under root C bar multiplied 1 minus C bar whole divided by N cap. But one very important thing is this, that while calculating LCL, if you get the negative value, then we have to consider LCL as 0. The average number of defects C bar is calculated by C bar is equal to total number of defects divided by total number of samples inspected. Now let us discuss about the Q-sum chart. This is a very interesting chart. A Q-sum chart is a control chart for variables data that plots the cumulative sum of the deviations from a target over a definite interval. A Q-sum chart requires only a pre-specified target value and a sequence of readings. These readings could be individual values or sample statistics, that is mean or average. The deviations of these readings from the target are added cumulatively and the sums are plotted sequentially. When these sums are plotted against time, a Q-sum line is generated which gives information about the trend in the process parameter. If the process is running on target, the line is horizontal, whereas the process of a slope indicates a change in the mean level of performance. These charts are ideal for detecting small shifts, that is 0.5 sigma to 2 sigma. In the process mean, they detect shifts in about half the time of shear charts with the same sample size. Now this is the diagram for the Q-sum chart. The diagram A, that is measuring the slope in Q-sum chart, and the diagram B is the slope guide. So this is how we can draw the diagram. So if for the sample size, if you calculate the Q-sum, so it is we can plot the diagram measuring the slope in Q-sum chart, and the vertical axis is the Q-sum axis and the horizontal axis is the samples. The Q-sum chart enables to identify that point at which shifts occur by determining the slope. The slope is the ratio of vertical distance on Q-sum axis to the horizontal distance between the samples intervals. Thus, in figure 6.7a, the slope at point A is 0.2 divided by 4, that is equal to 0.05, and at point B it is minus 0.18 by 2 equal to minus 0.09. The interval is chosen such that any genuine shifts in the process level can be detected easily. If the measured parameters is process mean, then by central limit theorem, any deviation in the process level is given by R bar divided by D2 under root n, where R bar and D2 are obtained from table 6.1 and n is the sample size. Twice this value is taken as the interval in measuring slope in the Q-sum chart. A slope guide is another tool for comparison of the slope at any point in the Q-sum chart. It uses a series of predetermined slopes as shown in figure 6.7b. Dear learners, let us discuss some very interesting numericals so that your concept will be crystal clear. The first numerical is the data for the test results of 20 samples are given in the following table. Each sample contains 100 items. Draw a control chart with 2 sigma limits in the process when the process is in control. So here there are 20 samples are given, and for each sample the number of defects are also mentioned. Say for example, for sample 1 the number of defects are 13, for sample 2 the number of defects 11, for sample 3 the number of defects are 8. So we have to construct the control charts, and if you count all the defects from all the samples, you will find the total number of defects is equal to 220. Now let us see how we can construct the control charts. Dear students, first of all we have to calculate the P bar. P bar is defined as the ratio of total number of defects during period and the total number of items inspected during the period. So here the total number of defects is 220 and the total number of items is 20 into 100 because the number of samples are 20 and in each sample total number of items are 100. So there is no problem for calculating P bar. So P bar is equal to 220 divided by 20 into 100, that comes out to be 0.11. Once you calculate P bar, once you know the value of Z, that is equal to 2, for this case we are considering 2 sigma level of process. So here first of all we would like to calculate the LCL, that is lower control limit. The lower control limit is equal to 0.11 minus 2 under root 0.11 multiplied by 1 minus 0.11 divided by 100. It comes out to be 0.05. Dear learners, while calculating LCL, that is lower control limit, you have to be very careful. If you get minus value, then you have to take 0, because minus defective items carries no meaning. But here you have got the lower control limit as 0.05. Now you would like to calculate the upper control limit. The upper control limit in the same way, but the expression is slightly different. So we can calculate upper control limit like UCL is equal to 0.11 plus 2 multiplied by under root 0.11 multiplied by 1 minus 0.1 1 divided by 100, that comes out to be 0.17. So that's why we have calculated LCL, that is lower control limit and upper control limit. So dear learners, you must be careful while calculating the lower control limit and upper control limit. First of all, you have to calculate P bar. After that, you have to calculate LCL. If it happens that the value of LCL comes out to be negative, in that case we have to take 0. After that, you have to calculate UCL. Now let us proceed for the exercise 2. This problem is also a very interesting problem. So this problem says that before supplying the circuit breakers to dealers, the quality control officer tested the lot size of 100 circuit breakers and found the average of 4, that is 4%, did not perform as per the specifications. Construct the P chart with 2 sigma control limits. So here the value of Z is given, that is equal to 2. The P bar you need not have to calculate, that is given as 0.04, and the sample size is given as 100. So all the values are given. Only thing you have to calculate the lower control limit and upper control limit with the help of the formulas given over here. Now the LCL is equal to P bar minus Z multiplied by under root P bar multiplied by 1 minus P bar divided by N cap. Here N cap is the sample size. Here it is given as 100, and P bar is given as 0.04 for this problem, and the value of Z is 2. So LCL is equal to 0.04 minus 2 multiplied by under root 0.04 multiplied 1 minus 0.04 divided by 100, that comes out to be 0.001. This value is for the lower control limit. Now the upper control limit is equal to P bar plus Z multiplied by under root P bar multiplied by 1 minus P bar divided by N cap. Here P bar is given, that is equal to 0.04, and N cap is also given, that it is 100. There is no problem for calculating UCL because P bar is equal to 0.04. The value of Z is equal to 2 and the value of N is equal to 100. So if you put all these values in the expressions for the lower control limit as well as the upper control limit, you will be able to calculate LCL. But for this problem, you will get the value of LCL is equal to 0.001 and UCL is equal to 0.79. Dear learners, if you see that in some problem the value of Z will not be given, but the percentage of area to be covered for this problem will be given as 95.5%. For that case, you have to take the value of Z is equal to 2. And if it is given that the percentage of area in normal distribution is covered 99.7%, then we have to take the value of Z is equal to 3, because the area under the curve plus minus 3 sigma with respect to the mean, it covers 99% of the total area under the normal distribution curve. But if the normal distribution curve is from mean plus minus 2 sigma, that covers around 95.5% of the total area. So if it is given that it is on the basis of 99.7%, you have to take value of z is equal to 3. Otherwise, if it is given as the percentage of area covered under normal distribution is 95.5, that is, for that case you can take the value of z is equal to 2. But my dear learners, for finding out the value of z, if the area of under the curve is normal distribution is given, so according to that area you can get the value of z from the statistical table. So now I hope that you will be able to solve any problems with regard to the control chart variables or control charts attributes. We are finishing our lectures, but let us summarize our discussions very quickly. We have discussed the control charts for attributes. We have discussed the P chart, NP chart, U chart, C chart and the Q sum chart. And lastly, we have discussed some numerical on control charts for attributes. Thank you very much.